In this video, we're going to go over a couple examples of finding limits of rational functions, and that's basically where you have one polynomial function, one polynomial divided by another polynomial, and these limits show up all over the place in introductory calculus classes, so it would be worthwhile to work a couple of these examples. Okay, so the first limit we're going to be looking at is the limit as x tends to 4 x squared minus 8x plus 16 divided by x squared minus 16. So just plugging in 4, and really when we're plugging in 4, we're basically seeing what happens as x gets close to 4. What do each of these terms get close to? Well, if x gets close to 4, x squared is going to get close to 4 squared. 8x is going to get close to 8 times 4. And 16 is going to get close to 16, right? Because it's independent of x. And then in the denominator, x squared is going to get close to 4 squared, and minus 16 is going to get close to 16. So we have 16 minus 32 plus 16 in the numerator, and we have 16 minus 16 in the denominator. 16 minus 32 is negative 16, plus 16 is 0, and 16 minus 16 is 0. So we have an indeterminate form here. If you recall from my indeterminate forms video, 0 over 0 is one of the indeterminate forms that you will see pretty often in an introductory calculus course. And this doesn't mean that the limit doesn't exist, just means that we have more algebra to do to find out whether or not it exists, and if it exists, what the limit actually is. So looking at the numerator, it looks like it's a perfect square, right? It looks like it's x minus 4 squared, and the denominator, hopefully you can see it's factorable into x plus 4 times x minus 4. And the numerator, x minus 4 squared, is basically the same thing as x minus 4 times x minus 4. And the denominator, you have x plus 4 times x minus 4. And here we can cancel these x minus 4 terms, and we're not dividing by 0 because we're concerned with what's happening when x gets really close to 4, but not necessarily at 4 itself. And division by 0 would only happen if x equals 4. We're concerned with the area around x equaling 4, but not quite at 4 itself. So this is just the limit as x tends to 4 of x minus 4 divided by x plus 4. 4 minus 4 is 0, and 4 plus 4 is 8. 0 over 8 is 0. So that's that limit there. Here we use factoring this numerator, x squared minus 8x plus 16, into x minus 4, the quantity squared, and then rewriting that as x minus 4 times x minus 4. And in the denominator, we factored x squared minus 16 as the difference of, as the product of x plus 4 and x minus 4. And that helped us cancel these x minus 4 terms that were causing a problem, giving us that 0 over 0. So we were able to get a non-zero term in the denominator. So we saw the limit's actually 0. Now we'll take a look at one more example. And it'll be, this one's going to be a limit as x tends to infinity. The limit as x tends to infinity of 2x squared plus x over 3x squared minus 5. Now some of you may be able to look at this and see that as x gets really big, this x squared term really predominates over this x term. Say x is like 10,000. Well, 10,000 squared, if you take 2 times 10,000 squared, right, let's say x equals 10,000. So 2 times 10,000 squared plus 10,000 is going to be some number, but that number can be conveniently represented as being approximately 2 times 10,000 squared. Because when you're talking about, if you're familiar with scientific notation, 10,000 is 10 to the 4th power, and you're multiplying it by 2. You're squaring it and then multiplying it by 2, then adding 10,000, which is 10 to the 4th power. So this becomes 2 times 10 to the 8th power plus 10 to the 4th power. And this 10 to the 4th power really becomes irrelevant when you have a 10 to the 8th power term here. So we say this is approximately 2 times 10 to the 8th. And in the denominator, you'll have this 3x squared. So say x is 10,000, you'll have 3 times 10,000 squared minus 5. Well, that's going to be 3 times 10 to the 4th squared minus 5, which is 3 times 10 to the 8th minus 5. So when you're dealing with something as big as 10 to the 8th, the fact that you're docking 5 from 3 times 10 to the 8th is really irrelevant. So this is really approximately 3 times 10 to the 8th. So when you have 2 times 10 to the 4th plus squared plus 10 to the 4th in the numerator, and 3 times 10 to the 4th squared minus 5 in the denominator, you basically have 2 times 10 to the 8th in the numerator and 3 times 10 to the 8th in the denominator. 10 to the 8ths cancel and you get approximately 2/3. So the limit's about 2/3, but so the limit is 2/3. As x gets bigger and bigger, these terms become irrelevant. X squareds cancel, and the limit is 2/3. But if you didn't see that, and that's completely okay, we'll take another approach, and I'm going to go ahead and rewrite this problem here. So the limit as x tends to infinity of 2x squared plus x divided by 3x squared minus 5. What we're going to do is divide both numerator and denominator by the highest power of x that we see here, and that's x squared in this case. So the numerator 2x squared plus x, we're going to divide it by x squared. Then the denominator 3x squared minus 5, we're also going to divide that by x squared. And remember, as long as what you're doing to the numerator, you're doing the same thing to the denominator, you are okay, because that's the same thing as we're basically multiplying and dividing by x squared, and that's the same thing as multiplying by 1. So you haven't really changed the number. We're just putting it in a form that'll help us evaluate the limit, and you'll see that here in a second. So 2x squared divided by x squared is 2. X divided by x squared is 1 over x. 3x squared divided by x squared is 3, minus 5 divided by x squared is 5 over x squared. And we didn't have to worry about division by 0 because we're concerned with the limit as x tends to infinity, and these are really large numbers. So when we divide by x squared in the numerator and denominator, we're not dividing by 0, we're dividing by a really big positive number. Okay, so as x tends to infinity, this 1 over x gets closer and closer to 0. Say, you plugged in 10,000. 1 over 10,000 is a really small fraction. If x were 10 million, it's an even smaller fraction. The bigger x gets, the closer to 0 1 over x gets. So 2 plus 0, this limit is essentially in the numerator 2 plus 0. In the denominator, we have 3 minus this limit, and okay, as x gets bigger and bigger, x squared gets even bigger. So, say x were 10,000, x squared would be 10,000 squared. But when you take 5 and divide by 10,000 squared, you'll get a really small number. But say x is 10 million. When you take 5 and divide by 10 million squared, that would be dividing it into 10 million times 10 million chunks. Well, the size of those chunks will be really small and will approach 0 as the number of chunks becomes bigger. So as x tends to infinity, this term will also tend to 0. And I should have said here, this term will go to 0 as well. So you have in the numerator 2 plus 0, in the denominator 3 minus 0, and that's 2/3. The same thing we got just by looking at these terms and realizing that as x gets bigger and bigger, this x term in the numerator and this -5 term in the denominator become increasingly insignificant. You're only dealing with this term divided by this term, and x squared divided by x squared. X squareds cancel. Don't have to worry about division by 0 because we're looking at the limit as x tends to infinity, so we're dealing with really big positive numbers, and you're left with 2/3.